Welcome back to our exploration of the quantum world. Today we're focusing on another key component of quantum circuits, the Z-gate. While classical gates like the NOT gate simply flip a bit's value between 0 and 1, quantum gates take things to the next level. They don't just manipulate probabilities as the X gate does, they also transform something uniquely quantum: phase. So what exactly does the Z-gate do? Think of phase as the color of a quantum state. Though it doesn't directly affect the measurement results, it's essential for how quantum states interact. The Z-gate introduces a phase shift, flipping the color or sign of the 1 state, while leaving the state 0 unchanged. This seemingly subtle change is vital for creating the interference patterns that power quantum algorithms. To understand this effect, let's visualize it on the Bloch sphere. While the X-gate rotates a qubit around the X-axis, the Z-gate rotates it around the Z-axis. A qubit in the 0 state stays unchanged at the top of the sphere. A qubit in the 1 state also remains in place, but acquires a phase shift. And why is this important? When a qubit is in a superposition, a mix of 0 and 1, the Z-gate phase shift dramatically alters the qubit state. For instance, applying a Z-gate to a qubit in the plus state transforms it into the minus state, a subtle but powerful change that underpins quantum computation. The Z-gate may not alter probabilities, but its ability to manipulate phase is crucial for unlocking the full potential of quantum algorithms. As we continue exploring the building blocks of quantum circuits, remember, every gate has its unique role in crafting the future of computation.